Assalamualaikum. My name is Nur Asfahani Ismail. I'm from School of Electrical Engineering, University Technology Malaysia, Skudai. So I'm here to present my paper titled Machine Learning Based Queuing Time Analysis in XGPON. So here is my presentation outline. So first, I'm going through the abstract of the paper, then introduction, the machine learning based DBA, delay analysis in XGPON, DANN modeling, results and discussion, and the last one is conclusion. So this paper presented a machine learning approach to predict queuing time in XGPON given the upstream arrival rate, the packet length, and also the upstream delay. Queuing time contributes to upstream delay and therefore would improve the network performance. For the output of the train ANN, it's perceived that for lower traffic load, which is from 0.1 to 0.5, and for higher traffic load, which is from 0.6 and 1.0, it shows that queuing time is higher by 30% and lower by 13% respectively. So according to the Global Internet Phenomena Report, there is an increase of 40% internet usage within the month of February and April 2020. So as the population of internet users are growing, the demand for high-speed stable internet connection is increasing too. So passive optical network is seen to offer cost-effective services and high-speed broadband internet access to the end users, which utilizes passive low-power components. For XGPON, the traffic classes are categorized into traffic container. There are 4 main traffic containers, which is traffic container 1, TCON 1, TCON 2, TCON 3, and also TCON 4. As seen in figure 1, this is a typical XGPON network diagram. So as you can see, PON consists of OLT in the central office, ONUs, and also passive splitter. The ONUs are connected to the OLT via splitter in tree topology. One of the issues in XGPON is dynamic bandwidth allocation, which determines the performance of a network. So listed in the table is some of significant machine learning based DBA. The first one is called DAMA. Uses PON standard of XGPON. The machine learning technique is K nearest neighbors. Key features, it forecasts additional bandwidth requests for each ONU. Second one is arrest. The PON standard is XGPON. The machine learning technique is reinforcement learning. And the key features is that it monitors traffic where underutilized ONUs are isolated for some time from traffic distribution to give the surplus bandwidth to other higher demand ONUs. And the last one is MLP DBA. The PON standard is EPON. Machine learning technique is artificial neural network. And this DBA predict bandwidth demand based on the status of ONU access point, whether it's on or off. So delay analysis in XGPON. So in XGPON, the OLT produces DBA results in the fixed frame duration of 125 microseconds. So there's a parameter called service interval, which indicates 1 DBA cycle and is represented in the unit of 125 microseconds. So the mean upstream delay consists of cycle time, queuing time, and also grunt time. So one cycle time, TC, is the time interval between consecutive transmissions from ONU. It determines the network average upstream delay. So figure 2 shows how OLT and ONU transmit downstream and upstream frame respectively. Okay. So for the queuing time, TQ is the waiting time of a frame in the queue. For our ANN modeling, the XGPON simulation used here consists of 1 OLT and 16 ONUs with uplink capacity of 2.5 gigabit per second. and ONU to OLT link rate is 200 megabit per second. So a total of 96 samples are collected from the simulation with normalized traffic load varying from 0.1 to 1.4. So the input features for the ANN modeling include upstream arrival rate, packet length, and also upstream delay. The output is the queuing time. For each TCON, the dataset is divided into 70% training, 15% test, and also 15% for validation. So the number of hidden neurons is 10. So here are the results obtained from the trained ANN. Figure 2 presents the queuing time attained using the trained ANN and target queuing time for each TCON. Target queuing time is actually the simulation of queuing time for each TCON. For testing purpose, input data of traffic load 0.9 is used. The train and queuing time for TCON 3 is very similar to the simulation. The train and queuing time values for TCON 4 shows a significant difference to its simulation values. It's worth noting that TCON 4 has surplus bandwidth, which means it's expected to have high queuing time. The train network for TCON 4 has been retrained for numbers of times as compared to TCON 2 and 3 due to its fluctuating target data. However, the trend for train ANN values follows target or follows the simulation of T3 queuing time, T3 and T2. It can be highlighted from the results that at higher traffic load or 0.9, it's more suitable to use train ANN with high traffic load range from 0.7 to 1.0 to achieve high prediction accuracy. So based on the learning history in figure 3, the learning process of the model takes 95 epochs to evaluate the accuracy and the loss of the model. So the mean squared error is used as loss function of the model, and the value obtained is 5.6117 as shown in the figure. So as conclusion, we present a machine learning technique, specifically ANN, to train and learn queuing time of ONUs in XGPON. We compare the train ANN results with simulation for TCON 2, 3, and 4. So the results show that the train ANN of TCON 3 queuing time has the highest accuracy as compared to TCON 2 and 4. The model evaluation shows a good fit, which supports the relevance of the train ANN model. The demonstrated train ANN will be improved to be applied in a DBA algorithm by predicting bandwidth demand. Here are some of the references used in the paper. Thank you.